Okay, so let's go ahead and get started. All right, so starting off with questions. All right, so I wrote them on paper this time so I didn't have to alt-tab back and forth. All right, so starting off, row 3, seat 2 to the, I got you last time, so I won't do you again. All right, so this is from a Poisson distribution, so it peaks towards the back. So people who sit at the back will get called on more. So I won't have Manjanath again. So, all right, so let's try again. Row 3, seat 3. And you are? Mia. All right, so what question do you have, Mia?
Okay, so I get that we're trying to maximize L, but do we have to are we maximizing L, I guess like the probability of each of the different categories, and then seeing which of those is larger?
Right, so what we're trying to do is we're trying to maximize L, which is the log probability of the probability of y given x. So let's decode this. And actually, so it isn't just any y and x, it's all of them. And so what this turns into is a sum over all of the examples of log of p of y I given xi. All right, so what is this? So that's I think what Mia's question boils down to. So does someone want to answer what this is?
Probability to label given the word.
Yeah, exactly. Or whatever your data are. So this is so we have label and we have data. Whatever it is, so it doesn't have to be words, it could be anything. So this is a conditional probability. And so what we want is we want to have good predictions of this guy given this guy. So, and this is mediated by our weights beta that tell us how to go from this to this. So we want to find the betas that do the best job of telling us what y's we have given our x's. So does that answer your question, or?
I think so. So L is kind of the collection of all of the best guesses for y based on x.
So the right way to think about L is as a function. Okay. So L is a function of beta, and given different betas, you can do better jobs of making this prediction than other betas. And so we want to find the best betas that tell us how to get from our data to our labels. Okay, all right. And, okay, and so now we have row 2, first seat to the left. And you are? Mohammed. All right. So what question do you have?
I'm not sure how to detect the best step size when you want to do the gradients.
Yes, neither do I. So yeah, it depends on your data, it depends on your regularization parameter, and you have to try out some stuff and see what works. So there's no right answer. Usually start small and work your way up until things break. But it's really data dependent.
Okay, so I think when you select the biggest step size, for example, in the beginning the slope is positive, and the next time your slope will be negative. So it means that you're going to the outside of convex. And you can do it binary and just make it
Yeah, and you can do that. You can have a decreasing step size over time, and that makes sense. That's one of the extra credits for the homework, so you can certainly try that out. It's a good thing to do, and there are even smarter things you can do, but just before you go down that rabbit hole, just try a constant step size and make sure things work with a constant step size. So, question? Yeah?
Yeah, so I'm wondering, so the update in the betas is always proportional, so the gradient is always going to be a magnitude, right? It's going to have a magnitude in the direction of the steepest descent, or ascent. So I guess I'm wondering if the step size, the learning parameter, could be a function of the gradient as well, like somehow taking that into consideration.
Yeah, and so there's a really nice paper by Ducci et al. Adagrad that goes into this in a lot more detail, and so it's not just so you're absolutely right. The current magnitude of the gradient should reflect how big of a step you take, but you also want to look at the history of the gradients that you've had in this dimension in the past. So, for instance, if you have a word like the, and let's say we're using text documents, that is going to appear in every document, and it's not going to be very informative. And so you're going to be really confident of your estimates for that. And so you don't really care about this too much. Whereas if you suddenly see a very rare word like marzipan, and you want to use that, and you've not seen gradients move in this direction before, you might want to be more flexible than you might be otherwise. So you're absolutely right. You can even prove some stuff about this, which they do in this paper. So good intuition, absolutely right. Little beyond the scope of this course to go into those details, but good intuitions. Yeah. Yeah.
So I haven't read the extra credit question, so stop me if I'm like going into it. But as far as gradient descent goes, kind of building off what he was having, a way to so it seems like there's different ways to change the step size that are appropriate, and I was kind of curious if we're doing gradient descent and we have like a upside down normal distribution, just for example.
Yeah.
And we just so happen to have a step size that is exactly the gap from one end to the other, and just completely skip over that. But at the same time, we're not changing our step size, so we're just going to be jumping back and forth. So like I was just like playing around with ideas of how to solve this, and so we could have like an algorithm that says, okay, we're getting the same height, with different x values back and forth, let's cut the step size in half, do something like that. But then what if we now have a W shape, and now that half point is exactly what we don't want to get?
Yeah, so one nice thing about logistic regression is that these don't exist for logistic regression.
Okay.
So it's convex, so it will always look like a bowl of some sort. And so the nice thing about convex problems is you can do a lot of stupid things. You'll still get the right answer in the end.
Okay, so we have a general bowl shape, but so does that also get rid of the possibility of a local minima?
Yes, exactly.
Okay.
Yeah, good question. All right, so I think we need to do one more. So let's see here, row 1, seat 3. So, and you are?
Dan.
Dan, okay. So what's your question, Dan?
Let's see, I guess, is there ways to, can you apply like reductions of dimensionality to the betas in order to find better maxima or stuff like that? PCAs or things like that?
That's an interesting question. So I don't know of anyone that's done that. So in a little way, this is sort of getting to deep learning. And so where you have sort of beta 1 coming from beta 0, and maybe beta 0 is of a lower dimension than beta 1. Right. So typically what happens in these cases is that you can get better solutions this way, but it makes inference much, much more difficult, right. And it loses convexity. So it makes things mathematically a little bit more difficult, but in terms of performance, you can get a little bit of a boost at the cost of a huge amount of complexity. Good question. Okay, yeah, and if you want to know more about this sort of stuff, Mike Moser will probably cover that in his neural networks course this semester. Okay, all right, so enough of random calling. What other questions do you guys have? Yep.
In regularization, when the beta is getting bigger and bigger, and then we use the regularization. So what's the problem if the beta is getting bigger and bigger?
Right. So you can have so what can happen is we're passing everything through a logistic function, and let's say we're getting everything exactly right, and so we have examples over here, and these are all positives, and these are all negatives, and we're getting everything right. So no errors whatsoever, because so 0 is right about here. We have pluses on the right, minuses on the left. Great. But remember, our objective function is the sum of log of p yi given xi. And one thing that you can notice is that you can increase the score by just shifting these guys over to the right a little bit. That guy moves to the right. That guy moves to the right. And this guy moves to the left. This guy moves to the left. This guy moves to the left. And you do that by making the betas larger, because so you want beta x, and so these are our vectors. So you take the dot product between these two, and that gives you the position on this line. So if you move these things further out from 0, you'll get a higher objective function. Does everyone see why that's happening? So everything agrees, and so it's not about moving things from here to here, and that's what should happen when you're doing learning appropriately. But all it's happening is just pushing things away, and so you'll keep increasing your score, but it isn't helping you solve this problem any better. You're just chasing probability without much effect. So that's all that's happening, and so that's one reason why you want to do regularization. Another reason that you want to do regularization is that it can help with overfitting. So you can have training error that goes down and down and down and down and down and down and down, but maybe your test error goes down and then maybe starts creeping back up again. And so regularization can help you stop a little bit earlier, so that you get test error of here rather than out here. So the regularization can stop you before you go chasing these crazy probabilities.
Is there any way to determine the lambda in the penalty?
Right, and so typically you'll do something like have a validation set, and so you try lambda, and then you have your validation error, and so 0.5, 0.1, 0.05, and then maybe this is 0.1, 0.07, 0.12, and then you choose this guy. And so you have a set of data that's different from your training set, different from your test set, and you choose your lambda based on how well it does on this validation set. Yep.
Sorry, for stochastic gradient methods, it seems that we don't need the whole data. I mean, we usually divide the whole batch to mini batches.
Yeah.
So, is it possible that we only use partial information if we have redundant information here? So, for example, 1,000. If we have 1,000 data points, can we have a test to be sure that if we choose independently 100 data points, it's enough for our minimization?
Yeah, I think there are rules of thumb about that, but I don't know that there are any sort of laws that you can actually believe in, and I think it's a lot like the learning rate. There are things that tend to work well, but you have to try a bunch of stuff out before you know for sure. So, yeah, so that's a way of not answering your question, I guess.
Excuse me.
Okay, yep.
In part of the lecture, you said when we have a streaming data or a big data, we're using the expected value just from the one observation. And I cannot understand why just one observation can help us for training and testing. I mean.
Right, so this is getting back to the previous question a little. So you don't have to use just one. You can use several, and this is called a mini batch, and that's quite common. The math is just a little bit easier with a single example. So the intuitive answer to this is the parable of getting from here to Denver Union Station. And so you don't need to survey everyone in the state of Colorado. How do I get from here GPS coordinate in ECCS to get to Union Station? That's way too much overkill. And what you can do instead is just walk into the first person that you see randomly and ask, which way is it to Denver Union Station? And so actually, so this is all right. So let's have a fun experiment. So everyone, close your eyes and point. So I can see your eyes. Close them. Close your eyes and point in the direction of Denver Union Station. So you have to point in one direction. So just point in a direction and keep your hands up. All right. Everyone needs to point. Everyone point. Okay, all right, so open your eyes, keep your fingers up, and look which way people are pointing. All right, so I think that...
North and south.
Yeah, so... okay, so you can put your fingers down now, and so it really doesn't matter that much. So when you're in this room, so one, this is a non-convex problem, so because we're in a valley, so it's a little bit more complicated. But if you followed the direction of everyone pointing their fingers, you would get outside the building, and then you'd run into someone else, and they could look at the mountains and say, okay, go away from the mountains, and then point you in somewhat the right direction. And then you'll start going east, you'll run into other people, then you'll start seeing, then they'll see the big buildings of Denver and point you in that direction, and then you'll actually get to downtown Denver, and then people actually know where Union Station is because all of the train lines and tram lines lead to Union Station, and you'd eventually get there. Sometimes people would tell you the wrong direction, like this side of the class. And that's okay, because you will eventually run in. The good thing is that people are not consistently wrong. If they're wrong, they're just pointing randomly. And that's fine. You won't have any sort of bias in your wrongness. You'll go in a wrong direction, but there are infinitely many wrong directions and only one right direction. And so as long as people are on average right, you'll get in the direction you need to go. Yep.
So what about like malicious data that would like, I don't know if this is a thing.
Yeah, and so that is a real thing, and so especially when you're dealing with things like spam detection, you actually do have to worry about that, because your spammers get to choose what data they generate, and they're generating most of the data. So you still need to be robust to that, and so that's a real issue. But for this class, we'll mostly deal with data from one distribution and not being chosen in an adversarial way. Yep.
To extend the metaphor a little bit, you might, if you're looking for directions, ask someone who look like they might know what the direction is, like a policeman or something.
Yeah.
So with regard to, say, a mini batch, would you maybe take that from a subset of data that you trusted more?
So people have thought about this. What seems to be the case in practice is that the effort that you expend looking for someone or some data that look like they'll be better is not worth your effort. And so just ask randomly and it'll average out, is what usually seems to happen. Yep.
So do you choose a point randomly from your test data to, like, how do you choose what point to update?
So not from your test data. This is how you learn your betas, but from your training set.
Yeah, training set.
You randomly choose from your training set, and typically in practice what you do, and if you look at the homework code, you shuffle your data and then just walk through it in order now that you've shuffled it. Yep.
So for regularization, using a cost function instead of a likelihood function, gradient descent, does that eliminate the need for regularization?
That's a tricky question. It helps a little bit. If you're saying something like hinge loss, so it does help a little bit. And so obviously you can't, moving these over doesn't help you a bit. That said, it does seem to help with the overfitting issue, but it's less important in practice. So it does help, you should do it, but it's not as important as for the logistic loss.
And how do you decide the constant, the mu, the regularization?
Yeah, so you try some out and you see what works. Yep.
Can you explain what clipping means, or like the non-zero dimensions for regularization?
Right, so I guess I don't understand the question. So
in the homework it mentions when we implement regularization, we need to be careful that we only modify non-zero dimensions.
Oh yes, right. I'll defer that question. I actually have slides on that when we get to an example on that. And so if it isn't clear at that point, ask again. Okay. Yep.
So my question is more a general question,
Mm-hmm.
the difference between discriminative and generative models.
Mm-hmm.
So I don't remember where I read this, but there was this comment that you can generate data using generative models.
Yep. By definition, yep.
So I don't understand why can't we do that with discriminative models?
Right. Okay. Let's talk about this for logistic regression. So logistic regression, that model is defined by some beta weights, and so let's go back to our spam classification example, and so we have Viagra +4. We have mother -5, and so on for every word in the English language. So then how would you generate an email from that?
fix, in other words?
Yeah, but how? So the issue here is that logistic regression gives you the probability of y given x, and it doesn't tell you anything about the other direction, and that's what we want to generate. So we want to generate an x. So how do you generate this x from these weights? And so that's a discriminative model can't do that. It just gives you the probability of y given x. Whereas if in the case of naive Bayes, we have the probability of spam, we have the probability of ham, and so 0.9, 0.1, we choose one of them, let's say it's spam, and then we need to generate some words in our document, and so we can say the probability of Viagra given spam, we generate that with probability 0.01, then we do that, and then we can generate every word in our document. And so the generative process, by definition, gives you a recipe for generating new data. Logistic regression only gives you the direction of x to y. It doesn't tell you how to actually generate all of the probability of x and the probability of y, the joint probability. It just gives you the conditional. So to generate data, you need the joint probability. In classification, we usually only care about the conditional probability, the probability of y given x. It doesn't tell us how to get the x just from nothing. Okay, yep.
So the objective function, so the first step was we identified that we should maximize the likelihood function.
Mm-hmm, yep.
From that on, there was you had expanded that function.
Mm-hmm.
Could you do the math of it?
Okay, sure. So this is a nice segue into what I wanted to talk about in discussion. Before I do that, any administrative questions about homework or anything like that? Okay, so homework 2 is up. Take a look at it. And so, oh, yep.
How to submit the homework through Moodle? I don't know how to.
Yeah, so go to the Moodle webpage. After I sent out the Moodle enrollment key, so after you've enrolled, then just go to the Moodle webpage and the assignments are listed. Click on the appropriate assignments.
Yeah, but how to submit the homework?
There are file uploads. So you upload your Python file, you upload your PDF, and that's about it.
Yeah.
Other administrative questions? Okay, so I encourage you to check out the Git repository and don't just manually download the files because all of the homeworks will come through the same Git repository, and so you can just do a Git pull to get the next homeworks, or if there are bug fixes or things like that, you don't have to keep downloading everything. You also get the data for free without having to re-download stuff manually. Okay. All right, so logistic regression. For the binary case, this is what the equations look like. And we want to do discriminative prediction, probability y given x. And we want to learn a beta given some examples. Okay, so our objective function looks something like this. And so when you take the log of this, you have this x over this stuff, and so the log cancels out on the numerator, but it doesn't cancel out in the denominator. So you're still left with this log here. And then when you take the derivative of this with respect to beta, now I don't have that slide here, but you can see that you're still basically going to have something of the form y of your example times beta I and times xi. So that makes sense. You have this beta I, and then when you take the derivative with respect to beta I, you're left with just yxi. And so you're seeing that in this part of the update here. So that's where that part comes from. And so this part is a little trickier. But the neat thing about this is that you can see that this looks a lot like the original form of probability of y given x. And so when you take the derivative of that, you basically end up time something of the form probability of y given x times x. And so that's the other part. So when you take the derivative of this thing, d beta, you get something that looks like this, and then when you plug that into your update equation, you then get probability of y given x times x. And then for both of these cases, you multiply it by your step size, lambda. Yep?
In the previous slide, where does the yj come from? That's underlined in the second line. There.
Yep.
Yeah, that guy.
Right. So this is what we're trying to optimize. We're trying to optimize the probability of the label given the example.
Right. But you got there just taking the log out of the probability function, right? Mm-hmm. Which is like the logistic regression function.
Yeah.
So just taking the log out of that, you get the
right, and yeah. So that's a little bit of sleight of hand, okay. And so it's because you have these two cases, the probability when so it's written in these two cases, but you can basically write this as yi minus something, and that something is the probability of yi given xi. So when you write it like that, you basically can write it in a form that matches both of these cases. Okay. So you take these derivatives, and then this becomes your update. And this intuitively should make sense. So you have a term, once you refactorize it, that looks like the difference between your prediction of this being y0 or y1, and you see how different it is from your actual answer. And so when you agree, when this prediction is close to the actual y, you won't change your beta much in this dimension. When it does look a lot different, you will change it a lot. So that makes sense. If you agree, don't change, you're happy. If you disagree, change it, something's wrong. Then the other part of it is you multiply it by the weight of your feature, and so that should also make sense. If you have nothing of this feature, your feature has nothing to say in this case. And if you have a lot of it, you're saying, hey, you were wrong. Here's why you were wrong, and the y being this x, and so you change it by that amount. And so you do this many, many times over all of your examples, and then you end up with a final answer. Okay, so that's the general recipe book. Let's go through an example. All right, so we have two examples, or two documents. One has y equals to 1, and one has y equals to 0. Let's initialize our betas all to 0. And so now we're going to step through and compute the gradient for each of these dimensions. So this is beta 0, beta A, beta B, and so on. Let's do our usual thing. So now talk to your neighbor and figure out what is the update for beta naught. And so I'll wander around and answer questions while people figure out what is a new value for beta naught, given this positive example. So this is the datum that we're taking the gradient with respect to.
Yeah. Let's justify that single. And using the step one, the previous one, 0 plus 1 times.
So I'm getting this right. Is
going to be the probability?
No, but
beta 0.
For this case,
So like one of them is right, right? Like
because the way the one is so the beta 0 the data points you have like x the probability of that y is associated with your intercept.
Weighted? Oh, I think that would always fill up the
unfortunately.
So x 0 4
Well, I think just
for example,
yeah, overall by that.
you could create an x it's but yeah,
Right. So that is on the left-hand side there. So you have 4 A's, 3 B's, 1 C.
Anything above here means 1.
Yes. Oh, yeah, yeah. Yeah, exactly. Yep.
But I don't know the value of
values of so the beta example maybe
I guess you just bound it by the
x which on 0
Okay, so what's the probability that this document is 1?
Yeah, all
Yes.
it ends up being
like
Yeah, because all of the betas are 0, so it says each of them with equal probability.
beta 0 again I'm not sure 0 plus 1 times 0.5
what's the probability?
I don't think I care about is what it was before 30.
I have homework 1 and I haven't started homework.
But what's the one?
x0 would be
For the positive example.
We don't care what it was.
Yeah, you could
So it has no effect. So you're searching right. So whatever we
an x.
so if it's 0, like x is same, and that would be
So that would be
no update.
letters.
Okay, my survey with my years seems to show that some people have completely got it licked, and some people are still struggling. So let's go through this. So first, the question is, what is the probability? So you take some input vector x. What will you always answer the probability of y equals 0 for that x with this initial beta? So what's the probability? So probability of y given x for all x, what does that equal to? Yeah, 1/2. So everything is, with the initialization, everything is completely even. You have no information. Probability of y equals 0, same thing as probability of y equals 1. No matter what your input vector x is, 0 times anything is 0. So it's completely even. So this is going to be 1/2 in any case. So how wrong are we for this example here? What is the difference between what we should be outputting and what we actually output?
1/2.
1/2. So it is 1, y equals 1. we're saying that with probability 1/2. So 1 minus 1/2 is 1/2. And so, and our lambda is 1. And how much of the bias do we attribute to the document on the left here? So what is the xi for the bias?
1.
1. So the bias is just something that's always on.
Is the bias.
And so we consider the bias to always be associated with every document, and it's not multiplied by any specific x. It's just always added in.
Could you talk about that a little more? I'm a little confused by that last statement.
Okay, so this corresponds to the bias.
Yes.
And so what x is it being multiplied by here?
1.
X0.
Yeah, the x0, which you can think about this as just being an implicit 1 that's getting multiplied by these guys. It's beta 0 always contributes to every document no matter what.
Oh, okay. This like we talked about this last
Yeah,
time.
exactly. Yeah. Yep.
Then are you saying that that y1 always gets the bias in favor of it?
Yes, exactly.
I thought I saw in the book that there's no difference between 0 and 1, and why not?
Yeah, but
in the book they actually had the equation switched around. 0 got the bias and 1 didn't get it.
yeah, and so all that matters is the then resulting sign of it. And so you can flip the sign arbitrarily to make it push you towards 0 or push you towards 1.
So it sounds like in this specific example we're giving y equals 1 the bias.
The better way to think about it is that positive values of beta 0 push you towards 1.
Yeah, so
you always get the bias, and it just depends which direction it pushes you, 0 or 1. I think it makes more sense to push you towards 1.
So like an empty set would be given 1, would be labeled 1 in this case.
Well, so given our initial, everything is 0, so even the bias is 0. So everything is completely even, 1/2 probability in both cases.
Okay.
So right now we have no preference. We're completely even, completely fair. Probability of 0, probability 1, both are 1/2.
Okay.
Okay. And what was our bias before? As I just said, 0. So 0 plus 1/2 times 1 is 1/2. So there we go. So this is our new value for beta naught. And so we've updated that. And so now let's move on. Yeah.
So I guess that was the question I was trying to ask.
Mm-hmm.
Why in the update does the 1 now get the favor of the bias? Like, why is it now an empty set would be labeled 1? Because
well, so we're not done yet. So you don't just so we've updated this coordinate, but we have to do everything. So our puny brains can only do 1 dimension at a time. But this is actually a linear algebra problem. You need to update, so we updated beta naught, and now after this we need to update beta A, and then beta B, and then beta C, and then beta D. And so eventually, so after this, we will have a push towards the bias term pushing you towards positive, but that's because we've seen one positive example. You'll see that a correction will happen when we see a negative example.
Okay.
Okay? All right, so now let's move on to beta A. And so let's compute the update for beta A. And notice that for beta A, you have 1, 2, 3, 4 A's in this document.
is the 1.
Probably.
Oh, the old one is 0. Plus 0 plus 1. Yeah, so it's just
Just need to calculate P.
1 minus half. It's going to be the number of. It's kind of confusing that the first one was x0 and the next one's xa. But I think that.
Well, so we know the probability.
No, just that xa is beta 0.
Well, so
Ours P.
Like you still have
so x. So I guess I don't understand the question.
I mean, I'm saying y of a so equals something. I guess.
Right. So we're doing stochastic gradient. So we're computing only the gradient with respect to this first document.
Or divided by
yeah. So unlike naive Bayes, it doesn't matter what your features are. They're numbers. You can and in fact one of the extra credits is to use TF-IDF instead of counts, and so this can be any real valued vector whatsoever. There are no constraints. Anything goes, and that's the flexibility of logistic regression. It can use arbitrary features rather than using probability.
Is this part of our?
Yeah, and you can multiply each of these numbers by the number of bagels you ate this morning, and if that works better, go for it.
Because there's 4 A's.
Why shouldn't we normalize it?
So what exactly is it? I'm so confused. Like xi, like is
Because for 0, we just solve it.
Exactly. Yes. Right. Okay. Yeah. Exactly. Yeah, and we'll get to the other one in a second. Yeah, exactly. Yeah.
I was just curious because I've been trying to look for
I think it was something.
yeah. I mean, I guess I see that.
Yeah. It's just for the document on the left.
Yeah, that's what I'm also.
So the last time specifically was like words.
Okay, so let's reconvene. All right. So what is P? 1/2. It hasn't changed. It's still this document on the left here. It's still 1/2. So that still remains the same. And so 1 minus 1/2 is still 1/2. The learning rate is still 1. So what is XA? 4. So that is different. And then the value before was 0. So that's like what we had before. And so what is the new value for beta A? 2. So 0 plus 2 is equal to 0. So 2. Okay. All right. So let's move through this a little bit more quickly. So beta B. Anyone have an answer for that?
3.2.
So okay, there are a couple of answers here. So let's walk through it. So y minus p is still 1/2, so that hasn't changed. And what is xb? 3. And so then we have 0 plus that, and so then that gives us 1.5. Okay? And so now let's do beta C. So,
quick.
1/2. I like that. So that's 1 minus 1/2, which is 1/2. And what is xc? 1. Only one of them. And so 1 times 1/2 times 1 equals 1/2. Okay. All right. And then what is beta D?
0.
Yeah. So and So it was 0 before, and then whatever we're going to add on is multiplied by xd, which is 0. So that's going to be 0. Okay, so now we've updated our vector. Yep.
So we should not use smoothing or?
Right now the regularization is 0. So we'll get to regularization after this, and we'll go through the whole exercise. Yep. Yep.
Is the choice of step size?
Yes, and in fact, this is a horrible step size. I chose it so that the math would be easier. And so this is a very, very, very bad step size to use. And it will push you all over the place, and it's a very bad idea, but I can't do math, so lambda equals 1 is a lot easier than other choices. So yes, it does matter a lot, and this is a really bad choice.
How would you
Yeah, so try out a bunch of different stuff and have some validation data and see what sort of held out error you get on your validation data, and then see which lambda gave you the best value. Okay. Other questions? All right, so we have now asked this random person how to get to Union Station. Let's now ask this random person how to get to Union Station. We have a slightly better idea of where we're going. We're no longer all 0. So now let's figure out what we do next. And so now let's update beta not in this case.
But now it's 0.
Yeah, that's right. We have, so we know that we have this new formula, right? So we just plug in, we know beta 0, and then we can just our, like, beta
P is now calculated based on
y. And we know that the B was from that. And then there's 3C.
I don't think you have to.
We know that that was 1 half.
So negative 1.
We're not looking at bias.
But we're not in, we're now we're looking at
Probability 1 is now.
so I was just plugging it into the formula. Except this then gives you like, there's not like a value of
The white ones, yes. The white ones. But beta not depends on the probability. J is one of the updated beta vector. Probability and y
but it should be like 1 half.
The update's going to be 0? Before the bias. I know.
Yeah, he is like that.
Sorry, say that again? So don't say prior, because that means something different. But not necessarily, because it also depends on the other features. And so, like, if you have a very common feature like the, some of that might get shifted over to the. But in general, yes, it will point in that direction. And certainly after seeing one example, it will point in the direction of whatever the previous example was.
Oh yeah.
Exactly, yes. 0.5. Yep, exactly.
That's probably 1 miles an hour.
Yeah. Right. And so it's just the luck of the draw. I mean, exactly, yeah. Yeah, and so it would be really bad if you looked at all of your spam documents first and then all of your ham documents, or vice versa. And so you need to shuffle before you start asking which direction you should go.
That's right. 0.5.
No, that requires a little too much cleverness for me.
And then 4 times.
Okay, so some people don't have computational devices, so let's reconvene and get a number. All right. So first, what's the activation? What is the argument to the logistic function sigma? So how do you compute that?
1 plus x.
So we want to compute the dot product of beta times x. So let's compute, and then that's the argument to the logistic function. So let's compute that. So let's compute this dot product. So how much does the bias contribute? 0.5. And no matter what data you observe, the bias will always be 0.5. How much does XA contribute?
0.
Yeah, because there are no A's in this document, so I won't even write anything down. So what does beta B times XB contribute?
1.5.
1.5, because there's one B. And then what does beta C times XC contribute?
1.5.
So it's this guy times 3, which is again 1.5. And then how much does XD times beta D contribute?
0.
0, because XD is 0. All right, so when we put that in, we get the probability of this being y equals 1 is 0.97, which is really, really wrong. So we're off by quite a bit. And so, oops. All right, so then, so the probability of this being 1 is 0.97. So let's go ahead and work through the update here for this new example. So what was beta naught before?
1.5.
1/2. And so then we add in lambda, which is still 1. And so if you're doing some sort of update of your step size, that might change, but let's just keep 1 consistently. And so now what is y minus the probability of y given x? Yeah, exactly. So we have minus 0.97 and then times 1. And so when you actually work out the math, so this is basically minus 1 at this point, so you'll get something close to minus 0.5. And so you basically flipped the bias, but a little bit less. And so because we have this really large step size, we're basically flipping the bias, but not quite. And so it's not quite negative 0.5, so if we kept doing this, we would eventually get smaller and smaller answers. Okay, so that's the update for beta naught. And so now let's do the update for beta A. Now that we know that y minus p is negative 0.47.
Well, there are 0 A's.
Is negative 0.97.
Same as it was before.
Hey, zeros. Everything's so easy.
Okay, so exactly, the probability of y equals to 1.
1.9.
Yeah.
Just 2 minus 0.97.
Yep.
Oh, right. So just 0.47. You update the whole beta vector?
Yeah, exactly. exactly, yeah. Right.
It is. Actually,
Yeah, yeah, yeah.
Why are we using
That's plus, right?
instead of?
Now it's
Like I think you can So
Y
Right. So this gets back to the question that was asked earlier. When we take the derivative, you can do y minus this, and so you don't have to consider two different cases. It should. Exactly. Yeah. So this should give you like 0.03. Yeah. So that's the right answer. Yeah.
Oh, okay.
Yeah.
I'm not that far. I'll be 2 plus 1.5, so it's 1.53.
Okay, so this should have been an easy one. So, what's the update for beta A?
0.
Yeah, you have no examples or no features to contribute to XA, so that's 0, so it remains exactly what it was before. 2, if you see an A, that means positive class. All right, so now let's do the update for beta B.
So beta B is constant the whole time. One.
No, it's
Yeah.
should be
No, so the original was 1.5, and you're going to
Yeah. No, I'm saying the update is going to be negative 0.97. Yes.
yeah.
It's times 1.
Yeah. And then we subtract that from
1.5.
subtract it from 1.5.
So,
well. If I had used
Roughly.
I think
Exactly why we don't use it. So 1.5 minus. So you guys can use it.
and I got it.
C will be 3 times. Oh, I got that as update. It's 0.7. This guy's 1. So 5 minus. And then not plus 2.
Yeah. Right, because it's y minus p, and so then you don't have to consider the two separate cases. And so in this case, when y is equal to 0, you have 0 minus the probability of y equals 1. And so then that gives you the right answer in what direction you need to do it.
Times of 97.
Because in the definition of logistic regression, you can say the probability of 0 equals to this, or the probability of y equals 1 equals to this, but it's easier mathematically when you take the derivative just to write it as y minus probability y equals 1, and it works out in both cases. Yeah. Yeah.
Okay, so we have 2.7.
Yeah. Right.
7 times 4. 3.88. Small. 3.88 plus 0.
I
Yeah, this is really easy. It's just like
definition.
we gotta start to figure out everything.
Yeah.
Even watching
So no, it's actually exactly the same. It's just your denominator has just more stuff that you add over, and so you just subtract off more stuff.
We're going to take
you have all sorts of pedometer.
No, you have the beta like that. Beta is like a...
Okay, all right. So let's walk through this. So what is y minus p?
And the slants here.
Yeah, so negative 0.97, and then the learning rate is still 1, and then how many xb's do we have? 1. And so what was xb before?
1.5.
1.5. And so now we're basically just subtracting 1. So we'll get something around 0.5, just a little bit more. So we still believe that beta B contributes to positive stuff because we didn't have very many of them. But let's see what actually happens when we get to beta C. Do people already have this answer? Should we just blaze through this, or? Yeah. All right. So, so let's do this more quickly. So we again basically have something 1 times negative 0.97, and then how many C's do we have? 3. So this is like subtracting 3 from what?
0.5.
0.5. And so that gives you something like negative 2.5, a little bit more than that. So that's now our beta C. And then how about beta D? So we have negative 0.97 again, times 1. And how many D's do we have? 4. And then what was this before? 0. So it's like we're subtracting. Oh, that's a 4. And so it's like we're subtracting 4 from 0, but not quite. And so we get negative 3.88. So now we have updated all of our vector, and now when we see D's, this very strongly points in the negative direction. Okay, so one thing that you might have noticed is that we didn't have to do any work when we didn't see a feature. And this is often the case, especially when you're looking at things like text. Not every document has every word. So you can be more efficient and just go through the examples that are non-zero. You can ignore the 0 examples. Okay, so this is the unregularized example. Let's talk about the regularized example before we do any questions.
Excuse me.
Yep.
Is there any difference if we started, from y equals 0, y negative instead of y positive?
Right, so I got a lot of questions about this. This is just so the derivative is easier. So instead of having to write down the 2 cases, the probability of y equals 1 and the probability of y equals 0 separately, you can just write down the y minus the probability y equals 1, so the math works out a little bit easier. And so it's just for notation.
Okay, and for the beta, should we, if we update, for example, if I got updated beta 0, and then I have a new probability, and then again I updated beta 1, and then I have a new probability. So do you think if we update it like that?
So this is the question that was asked earlier. Remember, this is basically a linear algebra problem where we're taking the gradient and taking a step along the gradient, and it only makes sense if you look at the entire vector rather than doing it coordinate-wise. Yep.
There's a lot of symmetry in the features. Is there any idealized? You ask both of the people at the same time, so then the bias turns out to be 0. The betas of the A and the D are equal and opposite. The betas of the B and the C are also equal.
Yeah, and so you could certainly combine these two together in a mini batch, and that's another way of doing it. It makes things just a little bit more complicated, and it doesn't always help. Sometimes it does, sometimes it doesn't. So you can certainly do that, and that's something people do tons in practice. You can also do some parallelism with that. But just for your first introduction, it's easier just to look at one thing at a time. Okay, so now let's talk about the regularized case. And so in the case of regularization, remember you're adding this term where you basically penalize the size of your beta squared. And so when you take the derivative of that, wait, why did I write plus? All right, so minus. So when you take the derivative of that, you get something that looks like this, where mu is saying how much you weight this. And so when you do that, you have this term. And you can basically think of this as a multiplicative update that just makes your betas smaller every time. So you do your normal thing, and then you make whatever betas you got a little bit smaller. So this just makes your weights smaller, but it makes it more difficult to ignore zero features. So in the case of unregularized regression, you could just only care about the things that are non-zero, update those, and ignore everything else. This makes it quite a bit more difficult because if in a particular document you don't see this feature, the derivative says that you should still multiply it by this. And so this can really slow down your execution time. Any ideas on how you might be able to get around this? Yep.
Just use a constant to,
So what do you mean use a constant?
Like just have some kind of constant that you would reduce on all parameters.
Well, so this is basically something like a constant. So this doesn't depend on your data. It doesn't care what y is or x is. So that's a good observation. So this basically is a constant, but you're still multiplying it every time. So that's no good. Even if it's a constant, you would still have to multiply it every time. So how could you get around that? Yep.
Could you just know how many steps you're taking and then raise it to that of its
Yeah, exactly. And so you can basically count how long has it been since I touched this beta last, and then just multiply this constant raised to the m power. And that gives you the update that you should have done had you been doing it every time that you should have been doing it. Okay, so this is our new update. Now let's go through this example with mu of 1/4 and our step size of 1. So let's figure out what the update is for beta naught.
Right, so can I ask a question about choosing mu? Is that something, again, that is sort of like step size that you...
But basically, so here there are some rules of thumb, and so mu should be larger the smaller your data set is, and the larger your data set is, mu can afford to be smaller. And similarly, the more...
What do you mean by large and small?
So it's also a function of the number of features you have.
I mean, just talking about, so is a fourth like a large value? I mean, I'm just,
Yeah, so a fourth is relatively large. Normally these things are like 0.1 or 0.01 or something like that. And also it depends on the number of features you have. So the more features you have, the more likely you need to have regularization. Yep.
What is the first value you have to consider for m?
Right, well, so it's just the first time you've updated it, and so on iteration 0, you should multiply it raised to the first power.
Since you updated it last.
You computed beta 0 before, right?
Basically, if you didn't need to update it for like a step, and the next time you updated it,
That's exactly what I did. Yeah.
raise it to the second. And that would like make up for the last time.
Okay, so we're running out of time, so let's go through this a little bit more quickly, and it seemed like people already had the answer, so what do?
That was like the last
Multiply
one.
the answer from before by 4 times.
So is it 1/4?
Oh, by half, yeah.
Yeah, so remember the derivative of x squared is 2x, and so that's where this 2x comes from. You multiply by 1/2, so we had 1/2 before, so times 1/2, and you get 1/4.
Well, couldn't you take in like the final answer from the last one after you sampled both the 1 and the 0?
Not quite, because now beta 0, after seeing the first one,
It's going to affect the calculations when you look at
exactly, it will change your activation when you compute the next one.
Okay.
Okay, all right. And so, as you can probably guess, so this doesn't depend on what y is, it doesn't depend on what x is, and so for all of the stochastic gradients with respect to this, we're just going to multiply what we had before by 1/2. And so then what do we get for beta A? So it's just what we had before times 1/2, which is 1. For beta B, it's what we had before times 1/2, so we had 1.5 before, so we have 0.75. Yep.
Then at what point can you skip that multiplication and then just multiply it by m times? Because it seemed like you couldn't skip the multiplication of 1 minus.
Right, so whenever the feature is 0, you can skip it. But if the feature is non-zero, you have to do this. And so you can never do it for the bias. So the bias will always get multiplied by this, by this term here.
Now get back to camp.
And so beta B, 1.5 goes to 0.75, and beta C goes to 0.25. It was 1/2 before. And what about beta D? Yeah, we don't care. So save it for later. And so now, so just very quickly, since we have no time, these slides will be posted. So when you go to the next iteration, you compute the activation. It's different from before because our weights are smaller. And so we make not as big of a jump as we did before. So before we made a very big jump in our beta weights. Now not so much, so we're less wrong than we were before. So now we're going to change in the direction of negative a little bit less because we're less wrong. And so for beta 0, we again do the update and we multiply by 1/2, and we get a smaller weight than we did before. And beta A, in this case, we don't care. We can save it for later. Beta B looks the same. Beta C looks the same. Beta D, however, is different. And so because we didn't mess with it last time, we raise it and square it. And so now this is a little bit different. And so here we needed to remember, when is the last time that I touched it? That was 2 rounds ago. And so you square it instead of multiplying it by 1/2. All right, so that's it for today. Next week, we'll do some more hands-on stuff and do feature engineering that will prepare you for the third homework.
He used to. Okay. I was working on. I'm just going in there.